I think we have Jamie, Kurtis, Magda, and Micah. 4 short talks.
Great, thank you so much for the intro. Yeah, so the thing I'm going to be talking about today is really quite nascent. It's something that I've sort of been poking at over the last couple of years on and off with my student Chloe Yang, and I want you to largely take away from this that there are some interesting questions here as opposed to us having like really good concrete answers. Okay, so you know perhaps for the benefit of my job security, right, and many other people in this room, training machine learning models is super complicated, right? And non-experts really, in an ideal world, would love to just like throw their data at like some kind of like abstract thing in the cloud, which is going to pick a machine learning model for them, which will then be like nicely automatically integrated into some kind of decision process, right? Wherein new data can be like run through this decision process, and the decision process, along with whatever model that was trained, by some large scale system where they had relatively little knowledge or expertise put into that system, could then provide them the ability to make a bunch of extra money. Right. This is what sort of the like best case scenario is for a lot of people who really would like to use machine learning for their particular task at hand. Right. They want to sort of offload all of that expertise about choosing architectures or choosing step sizes, or even really like the careful thinking about what it means to train a machine learning model. But there are two really challenging things that come from this sort of distributed sense of picking a machine learning model, right? The first of which is that the training system, right? Like if we're thinking about like training a particular class of models on some cloud system, right? Chances are the people who designed that have a much better sense of sort of how much additional training might improve the performance of predictions, right? Compared to the customer. And the customer might have a much better sense of sort of how much utility they would actually gain from the improvement in predictions that additional training or changes to the model might have, right? And this sort of information asymmetry is sort of a classic problem that comes up in lots of settings that involve economics, right? We sort of have one principal and one agent, and they have different information about sort of like what they would like to have happen next in some kind of game, and they have sort of different optimizations that they're thinking of. Right? And both the customer and cloud really would like to avoid wasted training cost, right? Which is to say, if a customer really doesn't have, won't get much additional utility for a model that involves a lot more training cost, maybe that's something that we would like to avoid. Right? And the fact that the system and customer know the different things really leads us to like interesting questions about, if we're at some point in like a training process, right? Should we stop or continue, right? If we're running gradient descent, is this a point at which we should stop or we should continue, right? And because basically one side of this market has information about sort of the possible improvements in accuracy, which you can think of that as the benefit, but also the cost, or that's part of the benefit, right? The other benefit is sort of how much utility a user would have from that improvement in performance, but that makes cost-benefit analysis very hard. Right? And there are some, solutions to this, or at least partial solutions when thinking about sort of how to design pricing for these sorts of issues. But it's, our understandings here are quite limited. The other part, which makes figuring out how to sell sort of machine learning training on the cloud challenging, is the upfront training costs might be super large, right? And so how should the training system charge customers to minimize wasted training, but also help customers find good models, right? And the current state of affairs, at least as far as I am aware of it, which granted I am not like a systems engineer, is that largely speaking, if you want to develop if you want to train an ML model, you pay for all of the costs of doing that upfront. And then once you have the model, you can sort of evaluate it as many times as you'd like, right? And that's sort of the best case scenario for the cloud platform that's doing all the training, right? They're not sort of extending any training for free to a customer. They're sort of recovering all the training costs all at once. But the customer might not be willing to make that large investment without having some understanding of sort of how well those predictions might work. Right. So that's all I wanted to say, right? That there's sort of very interesting information asymmetry questions that play intricately into the thoughts of how one might want to price training machine learning systems in the cloud. Thanks.
Thank you, Jamie.
Hi everyone, I'm Kurtis Heimerl, associate professor here in CSE. I'm going to talk to you a little bit about potential roles for the cloud and community-based private 5G. There we go. So a little bit of background on myself. I co-lead the ICTD lab here at the University of Washington. This is a long-running lab focused on technology and poverty alleviation. Traditionally, we've focused internationally, although there's a big domestic component these days, which you will see. Richard there mostly does HCI work, but I, and the reason I'm in this room, do internet access work, right? Like, how do we get the whole world online? I'm getting lasered, but I guess it's fine. Okay. And so our sort of flagship project is a thing known as the Seattle Community Network. The Seattle Community Network is a low-income access network in South Seattle and Tacoma. For people who can't afford internet access or devices or maybe don't know how to use these things, we set up actually a cell phone network, like a full-on cell phone network down there that's run by our community partners, which we'll speak to a little bit. I think the thing I'm most proud of with this network is that it's really a top-to-bottom solution. Like, we, in my lab, do core network designs, which we'll talk a little bit about core networks. But it goes from there. We actually do outreach, so the students go knock on doors, go make friends with partners, deploy equipment on roofs, and go all the way to training. So we actually run a system, program we call Digital Stewards, and this is where we train people from the communities to install and maintain the networks. And these have been deployed here among youth, adults. We've actually run it in tribal communities as part of the Tribal Wireless Boot Camp, which you'll see some photos of. So again, top to bottom, really happy about all that. Our partnerships are really important. Part of our dream is to say that what we want to do is have these organizations connect their communities. So we're really trying to build technology to empower them in that. And there's a wide variety of organizations. You'll see the high schools, Garfield and Franklin, some community centers, the Filipino one, as well as the Oromo Cultural Center, which is a mosque. There's some library branches, Skyway Library and the Tacoma Public Library. So really just like community organizations really focused on their constituents. I wanted to give a brief cellular primer because not everyone knows that, and it's somewhat of a big deal, something that does not get taught in a traditional undergrad networking thing, as it sometimes finds its way through. A cell phone network consists of a large number of access points connected to a thing called a core network. And this is often run in a data center. This is going to be the overlap that we have. This data center, for instance, the AT&T one is in North Seattle. You may have heard, I think it was 2019, there's an explosion in Tennessee where they took out AT&T's eastern seaboard, or maybe just southeast data center. And there's a big project out of Stanford called CORD, the central office re-architected as a data center, which is really trying to drag these folks from the telephone data center world into what all of you would consider the oldest hat. Like, just virtualization is the most arm-twisting thing to get a telecom to even consider, right? So a lot of 5G is actually just using kind of standard data center techniques at this point, but still a big advance for them and a lot of money being made. The core network handles kind of all the functions of a network that you don't have in your Wi-Fi network, right? So user authentication, mobility, the ability to move between access points, interconnect out to the other networks, things like VoIP services, all of these run in that data center and provide those services to the customers. And lastly, I think the most interesting piece is that there's a big push right now towards what's called private LTE or private networks. The idea here is basically, well, this technology is getting pretty flexible, pretty small. There's a number of important open source solutions that now can do it. We use Open5GS if anyone wants to look. And so we can now start to say that smaller organizations could similarly use these networks when appropriate. The standard pitch is, let's say you're running a factory and you want to have some like really high performance network on your factory floor. You're trying to do automation. You don't want to run Wi-Fi. Wi-Fi is not built for that in a variety of dimensions, right? So what you do is you go to one of these vendors and you install a private LTE network. So at the core of what our lab does is try to take these private LTE or private network designs and have them instead be used by community organizations to provide connectivity. That's sort of the thrust of what we do. Example of such projects, the CCNs are community cellular networks. On the left, you actually see my thesis work. It was a while ago now, but I still love the photo. People climbing a tree, putting up a radio. Center here, this is actually the Seattle Community Network. Here's one of the tribal wireless boot camp installations. And here's my most recent installation. You actually see me there with my student Spencer on a roof in Ulukhaktuk in the Canadian Arctic. Again, deploying a network in a hamlet there where there is existing LTE coverage, but it's like terrible. And so we can probably beat them and make people a little bit happier. So with all that background in place, kind of what does this have to do with the cloud? Well, I think an important thing to understand is our traditional answer space, kind of all of these projects are saying, let's move things away from the data center, right? Because we work in primarily extremely remote rural regions, connectivity out is really hard. And so trying to do any kind of communication out to the data center or the core network is just too painful. Like all of the signaling traffic, right, going over a 1 second link, it's just brutal. And so our big technical vision has been just pulling all that stuff out to the edge, hosting it locally, and that dovetails well with the community aspects of what we're trying to do, right? But these things are changing. Primarily things like Starlink, making it actually very possible to get reasonable connectivity out to these remote and rural areas. So we're just kind of curious to begin with doing what are known as cloud cores. There's a couple companies that provide them. Some of them are in the room. Amazon has a solution. There's an Azure-based solution. Even smaller providers, Bicell's Cambium, have solutions. And the idea of that is basically they put this big core network in a data center, and instead of you needing to run it in your own stuff, you just buy SIM cards from them and connect to them, and you're great, right? We're really interested to see if these kind of solutions and these new backhaul solutions make these cloud core systems possible for the kind of communities that we support. TBD, there's just like a large number of technical questions because, again, just these things were designed to operate singly inside of a data center and not across these kind of links. Similar to this, there's a big motion towards hybrid cores. This is just an advantage of 5G. They've started breaking apart the internals of what's going on inside of it. This is network function virtualization, all these kind of ideas. Again, brilliant new ideas to the cell phone people. And so what you've seen this as is local breakout or edge compute. The idea there is that for some reason 5G has decided their selling point is low latency. And so to do low latency, you simply have to place things on the edge. No matter how good your link is to the data center, it's not fast enough for edge, or for low latency, which it's, I think, ostensibly VR. I'm not really sure about the business pitch, but the technology pitch is there. And so now this technology enables us to not just move the core network to the edge, but actually break it apart, take individual components and place them in the community, and other components not in the community. We're really excited to explore how that'll look in the near-term future for us and the kind of solutions and communities that we work with. And lastly, I'm really excited to just think about what full cloud cores might look like, but not in a centralized way. A key thing of the way that we build networks is to not build bigger networks. What we want to do is we want to build more networks, right? More communities and more community organizations running these connectivity efforts. Instead of just rebuilding AT&T, we want to build 100 small AT&Ts and have them work together. Now, traditionally, core infrastructure is to say, like, let's build this giant service in the sky and I'll talk to it. Again, that's a cloud core. But for us, well, I'll say that centralized failure models are probably a bit overstating because data centers are certainly more stable than my community networks. You still want to have this ownership and this identity. And so how can we sort of work maybe more akin to a BGP kind of federation model in connecting these communities and setting up individual services inside a data center and still have them work efficiently, right? Like we're like friends, but not super close friends. What kind of stuff can be shared? What kind of optimizations will exist when it's not just one big service? So that's all I've got for you. I'm happy to chat more if anyone wants to. Otherwise, thank you. Yeah. I think
so. My ill-informed impression is that the telecommunications industry is extremely heavily regulated.
Indeed.
So what kind of, like, how is it that they're not, like, trying to sue you out of existence?
Oh, a couple things. So my first network, I just ran illegally. And if you're small, you can get away with it. But more seriously, my answer is easy. There's actually been a bunch of real fun movement on the spectrum side of things. So we talked for a long time about cellular regulations. The big one is Spectrum. CBRS is a big deal. It's a citizen broadband radio service. That's what we use. We're operating legally. It's wonderful. Our pain points right now are, I think, like 911 service, which is like you need to provide that if you provide VoIP service. We just don't provide VoIP service. We're like, use Facebook Messenger. I don't give a shit, right? Like, we're just like, make it all over the top, make it IP. It is not necessarily the answer that telecoms would want, and sometimes customers would want. You're right, but yeah, it's research. We're working through those things.
Curtis,
yeah.
Just so people know, why don't you mention some other places you put these things?
Well, so yeah, I mean, that was in Papua Indonesia, that one. Our big project was in the Philippines. We helped out with a network in Mexico and in Hawaii. We had people like stand up our stuff without us, which was super cool. There was one during COVID time in China, which we like got some emails and it disappeared. So we don't know what happened with that, but that was super cool. So really, just all over the place. There's a lot of communities that want to do this. Yeah.
Do you have any experience with Starlink? Like, do you have a feel as to the extent that it might enable all these community members to be connected to the core cloud?
Yes and no, right? So the places that we operate Starlink is not yet fully operational. We're gonna like sneak a terminal up into the Arctic, which I now have. Well, I know someone on the inside, which people could figure out pretty easily if they looked at my website. But that person has been able to say that like we could probably get service in the Arctic if we tried. And so now it's like at my dad's house, and I'm gonna ship that thing like 2 days from now. So we're seeing it's like really right at the line of this stuff being possible and it changing a lot of what we do. All right, thank y'all.
Hello, it's great to be here. I'm going to be talking about verification for the cloud. So the problem here is, how do you make sure that your cloud services and the programs running on them are reliable? Because cloud computing is really complex and it's important, it's mission critical. That means there's a lot of money riding on it, there are lives riding on it. So correctness is not an optional thing, you have to get it correct. So what are ways to get your code correct? Here are the standard ways that people use. You can do a lot of testing, you can use bug finding tools, you could do code review and design review and security review. The problem with all of these is, so all of these are great. I highly recommend them because they're good ways to eliminate some problems. Some problems. But if you've got something that happens once in a million, then that's happening many times every day. You're getting paged every hour. So if you really want to ensure that your code is correct, you need to do a proof. There are two types of proof that people generally do. One of them is proof of a model. That is, this is validating that your algorithm is right. And that's a great thing to do. But what you really like to do is have a proof of your code so that you know not just that the algorithm is right, but also that the implementation that's running is correct. And that's what I'm going to be talking about. Now, I'm not going to be talking about full formal verification of every single aspect of your program. I'm going to be talking about lightweight verification. So in particular, we're not going to try to prove everything about the program. We're going to try to prove something about the program, whatever thing it is that you're most worried about. And because this is lightweight, it's sort of proving a small property, you can run it over enormous legacy code bases. Or you can decide this is the only part of the code base that I really care about the most. Another nice thing about this is it's modular and incremental. That is, it assesses one file at a time. So after changes, you can run it on every compile. So this is a natural part of the development process, or part of your continuous integration. So I'm going to tell you about some things that we've already built. And maybe this will whet your appetite to either use these or to talk to me about other problems that maybe we can verify as well. So one is data integrity, checksums. This is very similar to something you heard earlier this afternoon, but it's taking a slightly different perspective on it, so it's complementary. This is entirely in software. Oftentimes, when you have a datum, you'll also be carrying a checksum along with it. The problem is that sometimes people forget to write one, or they don't compute it correctly, or they access the data without checking the checksum first, or they perform some operation incorrectly. So you actually have to perform it twice, not 3 times in this case, though there's no recovery. And we'd like to do all this without rewriting the code, without introducing new abstractions, for instance, about a checksum datum. I mean, if you're willing to rewrite your code, that's awesome. I actually strongly recommend it. But not everybody has that flexibility. So we built a system that does this and gives you a guarantee. And one cool thing about this is since it's entirely in software, it also finds programmer errors. It doesn't just find bit flips. But when people have, for instance, attached the wrong checksum to a datum. Another example is database keys. So if you have, you need to make sure that your database keys are legal. For instance, in AWS, think about bucket names. If you use the wrong bucket name, then you'll never be able to find your data again. And data loss is bad. So you need to make sure that those bucket names are legal and that they're the right ones. So we built a tool that gives you that kind of guarantee. A complementary to data integrity is data security. So one example is encryption. So you might want to ensure that your data is encrypted. That way, even if an enemy can get access to it, they are likely not to be able to decode it. So some standard requirements are that your data is always encrypted at rest, that is, whenever it's on a storage medium, that it's always encrypted whenever it's being sent on a network, that you use the proper encryption algorithm, or one of a set of approved encryption algorithms, that the key length is long enough, and then other things like you should always use HTTPS. You should never use HTTP. So these are all expressible as well. So there are other examples as well. For instance, you want to make sure that private data is not leaked. This is essentially the standard tainting problem. Another example is you'd like to make sure that there aren't any hard-coded credentials that are used in your system. And this here, with all of these, we're not talking about it's actually hard-coded at the place that you use it, but it doesn't flow from anywhere else to that location either. So one place we've had tremendous success is in compliance. So compliance is a requirement in order to serve certain types of businesses. For instance, if you want to handle credit card data, then you need to satisfy a regime called PCI DSS that's been published by MasterCard and Visa and Discover and Maestro and such. And some of the examples are ones I already gave you, like using, and you have to get a certificate from a third party. If you have that certificate, then you're allowed to process credit card data. If you ever lose that certificate, then you can't. And that can cost millions of dollars. So the programmers hate having to deal with the auditors, the third-party auditors. The third-party auditors don't enjoy it all that much, but they're getting a lot of money for it, so it's okay. So what we did was we automated this. So now, and the auditors actually accepted this. They said, if you can show me an execution of the tool, we will accept this and we'll give you the certificate. For those things, I mean, they also have to make sure that, the servers are physically locked up and that kind of thing. And our tool doesn't help you with that. So we've run this on over 60 million lines of code at a Seattle-based large cloud computing company. And I'm happy to say that the version of that code that is currently deployed has none of these problems. So those are examples of some tools we've already built. Here are some others that we've built as well. Verification that you have no resource leaks. That is, if you've opened up a stream or a socket, then you do close it down so you don't have a denial of service attack. And that's especially important when you have long-running programs. That you use the builder pattern correctly. That is, making all the calls that you need to. That there are no data races because you acquire locks properly before you access data. That all your code is properly internationalized, so you're not going to see hard-coded strings appearing. That there are no null pointer exceptions, et cetera, et cetera. So the secret sauce here is that we do this all via type systems. So we express the properties as types, and then the programmers just write those. The programmers are already used to writing types, and so it's easy for them to get it used to. We use a technique I developed called flow-sensitive type inference that makes it as powerful as the data flow analysis, and the annotation effort is low. I mean, you can tell because we ran this over 60 million lines of code. The annotation effort is much less than, say, writing generics. And whenever you write a specification, that's a machine check documentation that you can actually depend on. So it actually pays back for itself. And we're working toward making the effort 0 instead of low. So there's a Java implementation of this, and it's used every day on hundreds of thousands of projects at Amazon, Facebook, Google, Uber, many other companies as well. So that's lightweight verification. There are other, I'm really interested in anything having to do with programmer productivity. Anything we can do to help programmers do a better job more quickly, more easily, producing reliable software. So I've also done heavyweight verification with some of the people in this room. We have a verified implementation of a consensus protocol, and we have verified checking of BGP configurations. My group also does work on test generation to help you to increase your confidence, even if it's not going to give you a proof. And we're also doing work on log generalization, log analysis and generalization. Essentially, it's a machine learning technique that looks over the logs and then gives you data invariance, like this value is always in this range, or this list is always sorted. And it gives you temporal invariance, like you always call setup before you call process. And you can also look for violations of those as well. So that's all I have to say. I've talked about mostly lightweight verification, though other things, to give you data integrity, data security, and many other properties. All of these properties are expressible if you have if you're looking at it in the right way as simple type systems. And so if you'd like to talk to me, I'm happy to take questions now. And I'm also, I'll be around, and I'd love to talk with you later. Hank.
Is this compiler-based or independent tools, or both, or neither? Or?
Okay, so the Java implementation is a plug-in to the compiler. So Java's compiler has a plug-in mechanism, and the Java language added type annotations, which was inspired by my work. That's why it was added to the language, because they wanted to be able to do this kind of verification. So it's neither in the compiler nor a separate tool. Other questions? Okay, thanks a ton.
Last we have Magda back as a database researcher hat.
Awesome, everything. All right, well, good afternoon, everyone. It's so exciting to be back here. I hope everyone had a good day, and yeah, you're excited to see kind of some of the final presentations. So now I'm taking off my director hat. I almost said that I should take off the jacket and put on a sweatshirt, but I forgot. I'm really wearing here my professor job, so my professor's hat, and really my area of expertise is not really on cloud infrastructure, but much more kind of a little bit higher up the stack, looking at data management systems and all kinds of, cloud database systems, whether it's for typically for analytics, but kind of looking at different components. And in this project, we are really looking at kind of machine learning as workloads, and how can we best support machine learning workloads from the data management perspective. So really looking at the data management aspects of machine learning and exploring the cloud as kind of a great platform. So first, acknowledgements that I'm going to talk about two projects that we have done. Both are led by my graduate student, Dong Hei, who I believe is on Zoom. And also the first project was done, we did it in collaboration with Maureen Down and Walter Kai, who graduated. So to all the students in the room, yes, people do graduate sometimes, which is great. And well, you never know. When you start, you kind of, and then when the second project is currently in progress, and that's a project we're doing with Jaeyu Zhang, another student who was just giving his quals presentation right now, and then Alex Ratner. So what is the problem? So as we know right now, we know that deep learning is really, achieving kind of great, phenomenal success in so many different application domains. But we also know that deep learning can be a black box, and opening that black box, understanding what models are learning, how they are working, is really important for many applications. So it's important to understand why, for example, a deep learning network might misclassify something, or it's important to understand what that network is learning. So here are some examples. So this is a very example kind of in a standard character from the MNIST data set. And this is actually a 2, but it was predicted as a 7. And we might be interested, like, as a user, well, okay, why? It kind of could go both ways, right? It kind of has the peaky angle of a 7, but it also has kind of the round bottom of a 2. So you might want to understand why did the network think this is a 7. And if we look at some explainability techniques like saliency maps, we will know that some of the pixels that were most important for this classification results were actually the ones kind of showing the really focusing on that kind of sharp edge. And there are also many other examples like that. So here's an example from a recent paper that came out of our computational biology group here in the Allen School. This is a paper that appeared in Nature Machine Intelligence. And what they did, which is very interesting, is they looked at a lot of models people had deployed to take chest X-ray images and classify them as COVID or non-COVID. But the challenge is, of course, to kind of train such models, you have to have a good, training, validation test data set. And to collect these data sets, people had to get data from different hospitals. The problem is, of course, different data sources means there's going to be kind of artifacts in the images that are unrelated to the pathology of the lungs. And what they have shown actually in this paper using these kind of similar explainability techniques is indeed a lot of those models were classifying images very well, but they were not looking at the lungs, right? So kind of the darkest pixels are these artifacts. So the models were learning very well how to distinguish the source of the images. So again, kind of an example where explainability is really critical. And there's also a whole area of people trying to trick models into misclassifying images, so submitting, for example, adversarial images, like in this case, classifying shirts versus other pieces of clothing. But we also saw examples with if you take a stop sign and you put just the right kind of stickers on it, you can cause machine learning models to misclassify them, which can have, of course, kind of really bad consequences. And again, a place where if we understand where the model is looking, what the model is looking at, this can be really helpful. So all of this is kind of really cool machine learning, but my claim is that a lot of this actually really does become a data management problem. The problem is, in order to kind of as interactively as possible do this kind of debugging, understanding what the models are learning, it really requires either one of two things. We need to generate all of these debugging artifacts, and then there are really two choices. So either we generate them ahead of time, or we have to compute them when the user is asking questions. So here's kind of a graph that shows an example where we looked at not even saliency map. This is an example where we're looking at just activation values in a deep neural network and trying to kind of ask queries about these activation values. So if we take this example and just pre-generate all the activation values for the examples, then we have kind of these circular points that show that the query time for asking questions is really fast, but we have really used like more than 1 terabyte of storage, which is quite significant. On the other hand, if we say, no, well, the user will not ask questions about everything, and we don't pre-compute anything, and we only compute what is needed on demand, then the queries really slow down. So we have queries that can take like, a minute, 2 minutes to process, which is really not the kind of interactive, pleasant experience. And if now, instead of looking at one model, we have kind of a cloud system, we're training a collection of models, we want to compare what these models are learning, then that problem amplifies. So what we have done is, the first thing is we actually built a system called Deep Everest, and that system was really looking at one specific kind of queries, which are called interpretation by example queries. So the idea here for those queries is we have kind of a deep neural network that is doing some kind of classification task, and what we want is we want the ability to look at different layers and understand, right, the pattern of the activation values for a given example for certain layers, and then we might want to compare it to others. In our example of this digit, right, we might see, well, why is this 2 being classified, as a 7? We kind of can look at the saliency map, but we can also see, well, for different layers, certain neurons are really activated for this example, and we might want to know not only for which layer, which are the most important neurons, but also what other images have the same kind of pattern of activation values. In this example, here are kind of the 2 most similar images according to this activation pattern. So Deep Everest enables users to really limit how much storage they want to use to pre-compute these kind of tasks, but still kind of provides really good experience, kind of very fast query execution time. There's more kind of information on our website. We have the paper, we have the code. The paper appeared last year at PVLDB. The key idea was that in Deep Everest, what we have done is we kind of pre-compute, so we do some pre-processing ahead of time, where we look at the data, we compute the activation values, but instead of just storing them on disk, we actually kind of cleverly index them in a kind of very compressed fashion, such that we remember kind of for each neuron separately, kind of where the different examples are falling in terms of kind of ranges of activation values. And that, coupled with a clever algorithm, allows us to only pre-compute during query execution kind of the minimum amount of activation values we need, and really allow kind of the queries to be answered very effectively. So here's kind of the key motivating experimental result, which means you can see we had like the idea of pre-computing, storing everything on disk. Those are the circles, and they use a lot of storage. You have the squares. That means I'm going to compute everything on demand. And if you look at what our system is doing, it really kind of gets the best of both worlds. Yes, we do some pre-processing ahead of time, but we only use a little bit of storage on disk, so people can hopefully do this kind of in a very easy and inexpensive fashion. So this is just one example and one project that we completed. Where we are going now with this is really to expand this idea. So now imagine that instead of having just one model and we want to understand what that one model is learning, we are typically kind of in many, I think for all of our projects, right, when we try to train a model, we're going to train a model and then we have like the best architecture. We might try to have maybe like a much simpler architecture because maybe we want to run it on the edge. Ultimately, we can try to compare it on different hyperparameters. We want to do some tuning. And then we really want to understand, okay, how are these models differing? Or in the case of like this example from the COVID X-ray image analysis, different teams might be generating different models, and it's important to understand, are these models different? What is each model learning? How do they differ? So then we end up with a setting where we have lots of models that we're training. All of these models, we can generate a large amount of these debugging artifacts, and we want the user at the end to be able to ask queries in this interactive fashion and really compare the models to each other and understand what's going on. So the settings that we have, all of these, especially we're now currently looking at the saliency maps because they're really effective in terms of the user output and finding ways to support queries that allow us to combine, aggregate, and operate on these efficiently. So this is a work in progress. The way that we are viewing the problem is really, you can imagine you have a view that is not materialized. So we have a table, but it doesn't actually have any content. But the user assumes that it contains the saliency maps for all the images and model combinations. And the user wants to ask questions such as, well, from that map, I would like to maybe look only at images that were misclassified in a certain way. And I would like to get their saliency maps that maybe I can aggregate. So perhaps for one image, I want to understand how much the models differ in kind of the pixels that they're looking at for those images. And I want to see maybe the top 3 or top 4 or some, kind of top number of images in this case to really be able to understand the trickiest images that maybe the models are struggling with. So this is a beginning project. It's a new project we started not that long ago. We're looking at all kinds of optimization. So how can we leverage what we know about the queries to try to avoid computing the saliency maps? Can we leverage caching? How can you leverage distributed computation efficiently? So I'm happy to kind of, hear people's thoughts about this project and, just talk about this project offline if anyone is interested. But in general, kind of in our current project, we're generally broadly thinking about machine learning and these tasks, especially of debugging, explaining, understanding what the models are doing, because those tasks are truly the ones that are the most data intensive, and how can we use data management techniques to accelerate and support these tasks. All right, that's it. That's my lightning talk. Hopefully you enjoyed it. Thank you. So happy to take any questions now or offline.
So super cool work and very important to help people understand what the model's training on. You used images as an example, and I'm wondering, that sort of makes it easy for us as humans to understand and do the saliency map comparisons, things like that. Are the ideas applicable, or have you thought about how they go for higher dimensional data, like just general vector sets, or like audio files or something that's not?
That's a really good point. So right now we're looking specifically at images because there's just so many examples from like sciences, from different domains. So this is just kind of a topic of interest to us. But I think that definitely at the end of the day, from the data management perspective, they're just like arrays of pixels. So definitely a lot of the optimizations can hopefully be adapted to other shapes of arrays of pixels than images. Yeah. Other questions or comments?
So one thing
about interactive debugging is often you want to, like, you're sort of surfacing the goofiness that you might not like, but then you need to be able to make a change and then try again. So it seems like in this domain, though, making a change might require retraining. Is there, like, how do I close, like, so, you know, you're making that problem visible, but what do I do next? Can I, like, edit, recompile, go again, or how
exactly, and this is actually part of why this is such an interesting problem to do in a cloud setting, because in a cloud setting, I have access to clusters of resources. So while I can use, for example, one machine where I have my model right now in a snapshot, and I'm getting the debugging, I can easily start to launch some retraining mechanisms on other machines, other instances, and then the interesting question is, okay, well, the user doesn't want to wait, and that has to happen. So when do we retrain? How do we retrain efficiently? Is also kind of interesting. And how do we leverage that kind of large scale of the cloud to do this so that the user perceives something as interactive as possible without going bankrupt? Because at the same time, you know, you want to put a cap on the budget.
Yeah, when I do like make thing make, my bank account goes to zero, it might not be, but yeah.
I know, yes. So actually many years ago, I had a student. We were like just starting with a cloud. That was many years ago. And we were running some experiments, and one of my students said, well, a cloud, how expensive can it be? And exactly, it was $40,000 by the time he realized the cloud actually is expensive. So, but you know, thank you Amazon for forgiving that error.
All right, thank you, Magda.
All right, thank you.
All right, I want to thank you again. We're really happy all of you could make time and come here, support us, give us feedback. So hopefully this will kind of go in what we do next, and we'll definitely consider everything again. Thank you. Yep.